This conference will now be recorded.
Hello students, very good evening. We are continuing discussions on the previous year's questions on the modern physics part, where we are discussing questions from semiconductor, atom, nuclei and photoelectric effect. So today we have some questions from previous year's JEE papers. So we'll start from here. So we'll just read the questions and try to solve them one by one. I think one or two more lectures will be there on this particular topic, because there are diode and digital electronics part, and basically on the transistor part we have not discussed much. We'll pick up some good questions from previous year's paper in this week in the next class. Okay, so let us read this question and solve. If a star can convert all the helium nuclei completely into oxygen nuclei, the energy released per oxygen nuclei is. So here you have to understand this question that, and you can see the mass of the helium nucleus is given as 4.0026 AMU, and mass of oxygen nucleus is given as 15.9994 AMU. So here you have to understand this question in this way, that if helium nucleus has to be converted into oxygen nucleus, how many helium nucleus you may need, that you have to first find out. Let me tell you what I'm trying to say. Suppose helium nucleus, it has 2He4, right? 2He4, whereas oxygen nucleus, it is 8O6, right? So to get one oxygen nucleus, how many helium nucleus will be required? So 4 such helium nucleus will actually give you one oxygen nucleus. So now it is easy. See, now what we'll do, we'll find out the mass defect. So mass defect is denoted by delta M. So mass of helium minus mass of, so I need 4, right? So mass of helium nucleus is this. For creating one or getting one oxygen has this much mass, so there is a mass difference, and this mass difference will actually manifest as energy, or released as energy, that will be released by this particular reaction as energy. So this mass defect will get converted into the energy. Okay, if we try to do this calculation, you know what you will get. It will be 0.011. Okay, now if you convert this mass into energy unit, because here you look, the options are given in the energy unit, and also the energy released per nucleus, per oxygen nucleus you have to calculate. So we have to get the energy released is delta M mass defect into 931. This will give you unit of MeV. So if we multiply this 931 with this mass defect, what we get is 10.24. There is some 1, so there are second up to second decimal will take, so 10.24 MeV. So this is the energy released in this process, in this nuclear reaction. Okay, I hope you have understood this. And see, option C will be, or third option will be the correct answer for this question. So here this particular part is little bit actually confusing for us. See, if a star can convert all the helium nuclei completely into oxygen nuclei, so you have to understand that by saying this, they are asking you to find out the formula. Okay, so suppose a helium nucleus is completely converted, so then how many helium nuclei will be required to get on one oxygen nuclei? So that you have to first understand. Okay, we'll move on to the next question. So this question is also from JEE mains paper 2013. That's very interesting problem. You see, the question is, in a hydrogen like atom, okay, hydrogen like atom, an electron makes a transition from an energy level with quantum number n to another quantum number n minus 1. So let us say one hydrogen like atom is there. There are many levels obviously. So suppose this is the ground level U1, this is E2, and this is E3. Here n is some, suppose this is index n and this is some n minus 1. Okay, n minus 1. All right, I could take anything anyway, so I'm just taking now, let us say I'm taking this as n and this is n minus 1. So it will be just ulta. This will be just opposite, n minus 1 here, and this is n. This is higher level, this is lower level. So an electron in hydrogen like atom was here in nth level. It is making a transition n minus 1th level. Then the frequency of radiation emitted is approximately equal to how much? Okay, so you know energy is always directly proportional to frequency, because E is equal to h nu, we know that. And see, for hydrogen like atom, you know, the energy will be minus 13.6 into z square divided by n squared. Okay, this is the energy. So now the frequency, if you want to find out the frequency of the emitted radiation, then you have to first of all find out E is equal to h nu, right? So if you want to find out nu, then you have to find out the difference in the energy between these two levels, and then you have to divide that with h. Okay, h is the Planck constant. Okay, Planck's constant. So you have to do this. So to get this difference in energy, we need to know the energy of each level. So suppose this is the energy for En, and this is energy for n minus. Okay, so 13.6 n minus 1 whole square. This is z square, because this is hydrogen like atom, not the hydrogen atom. If it would have been hydrogen atom, then z is equal to 1. This you know. Now see, we have to find out nu. Nu means I am just taking just difference between the energy level, the energy of the energy level divided by H. So this is what I have to do. Now you have to find out approximately proportional to, not the exact value. Then I can just think this as K. So look what I can write delta E as. I can write delta E energy difference as K, okay, K by n minus 1 square, okay. I'm just taking the difference minus of K by n square, okay. If this is the case, then look what we get. We'll get K into 2n minus 1 divided by n square n minus 1 whole square, okay. If we take, see, there is one condition given here, we can make use of this condition. So if we make that use uh, of that condition, then we can neglect this 1. So 2kn, and here if I take n common, then it will be n to the power 4, okay, 1 minus 1 over n. So this term can be neglected because n is much greater than 1, okay. So since n is much greater than 1, so we can write delta E by H is equal to nu, okay. So that is equal to nearly 2k by n cube. This term I have taken as not 0 exactly, I'm just taking this term 0, means this term is actually okay, so this is fine. All right, now this is directly proportional to 1 over n cube, n cube, okay. So look here, the D, option D will be the correct answer in this question, okay. Sometime you may feel, what is this question here? Actually, see, energy is always uh, inversely proportional to the n square. Then obviously energy and frequency, they are directly proportional to each other. So you might be thinking that this is the correct answer, but here we have to take the difference, okay. So we have to take the difference. So in the difference in energy, this frequency will not have this particular variation 1 by n square. It will be 1 by n cube, as we have derived here, okay. Now we'll move on to the third question. You can see this third question is given from LED. This is actually 2000 IIT JEE 2000 main question 2013, okay. What is the question? The question is that IV characteristics of LED is. See, here I'll tell you, these questions are actually informative. You have to remember some of the characteristics of diodes and LED, solar cell, etc. For them, you have to, some characteristics, IV characteristics, you should be familiar with. So in this case, LED always works in forward bias, works in forward bias. So this is a one point which we should keep in mind. So among all this, you look, this is not forward bias, this is gone. Now forward bias, see, LED is actually a diode, right? You know this diode has PN junctions, right? Diode has P and N junctions, and at these junctions, you have the positive ion cores, this side positive ion cores, heavy positive ion cores, and this side negative ion cores. So when there is a forward bias given, excuse me, so when there is a forward bias in the circuit, that means P is connected to the positive terminal of the battery, then what happens? Charge carriers from like holes from here will try to cross the barrier, and electrons will try to come towards P side. Anyway, there will be this kind of diffusion current will be there. Anyway, so in this case, what happens when an electron and hole recombine? Okay, if they recombine, this is positive charge character. So if they recombine, there will be emission of energy. Emission of energy. Okay, and that energy will be radiated as some light. Some maximum cases it may be in the infrared region. Nowadays there are blue LED, white LED, etc. So in this case, you know what happens. Forward bias characteristics of diode is similar to that of the characteristics, IV characteristics of LED. So in this case, you look for an LED, for a diode, which one is the forward IP characteristics. So that you have to analyze. So you look, this is the correct one, because you know current in case of PN junction diode, forward bias goes like this. Okay, so this is I, this is V. In forward bias, current goes like this. So this is actually the IP characteristics of LED. Okay, so because of recombination of electron and hole, there will be emission of energy as radiation. Okay, all right. Now we have similar question like this. Identify the semiconductor devices whose characteristics are given above in order A, B, C, D. See, A, B, C, D, there are 4 IV characteristics, or 4 graphs I can say. Out of them this 3 are IV characteristics, and this is intensity versus resistance, intensity of light versus resistance. Okay, so here there are devices like simple diode, Zener diode, solar cell, light dependent resistor. You have to match. Suppose this one for whether it is for simple diode or for LED, Zener diode, for solar cell, or a light dependent resistor, or something else. So like that, A, B, C, D, which one is sequentially? See, in this case, sequentially, this is obviously, you can understand, this is a simple diode, right? This is showing the forward current, this one, and this way it is actually reverse saturation current. It is independent of voltage, that we know. Okay, and this is the forward current for a simple diode. So this can be assigned to simple diode. And you look, this is very well known for us. This is Zener diode because at the breakdown voltage, okay, and at the breakdown voltage, which is denoted by Vz, there the current will be actually increasing very sharply. Okay, very sharply it will increase, and even if there is a fluctuation in the breakdown voltage or applied voltage around the breakdown voltage, the current is never going to change. So this is Zener diode. So look here, here it is illuminated. So the diode is illuminated. So you have got two curves. One is dark current. These are actually uh, the dark currents. Okay. So illuminated and dark current. Actually, figure is this like this, and this is there in the original question, and this is a question 2000 IIT JEE 16. So here this current is, some current is called dark current. Okay, so dark current, this word comes only for solar cell. Whatever you have read in your textbook, NCERT textbook, you'll see dark current is mentioned only for solar cell. Here, therefore, so solar cell output is actually composed of two currents. One is dark current when the cell is not uh, biased properly or disconnected, and then the real current will be obtained after connecting or biasing properly. Okay, now this one is obviously light dependent resistor. You can see as the light intensity increases, the resistance decreases. This means what? Okay, so here this is for light dependent resistor. Resist Resistance is decreasing with increasing the intensity of light. So that's the question. And you look here sequentially, this is the simple diode, this is Zener diode, solar cell, light dependent resistance. So this is how this first option is correct option. Now we'll move on to the next question. So these are questions which are actually informative questions, not very elaborate kind of questions, or not very very much calculation is involved. See, in a common emitter amplifier circuit using NPN transistor, phase difference between the input and the output voltage, this you guys know, this is 180 degree. Without reading the question second time, you can just do that. Okay, so always in the amplifier circuit, you can amplify the voltage, but amplified voltage or amplified power will be in the opposite phase. There will be 180 degree phase difference, 180 degree out of phase. So output is 180 degree out of phase, in an amplifier amplifier. Okay, output of an amplifier C or N, this is NPN transistor amplifier will produce actually output which is 180 degree out of phase. Okay, so now we'll move on to the next question. Okay, so this is also a very good question. We'll try to understand the question and try to solve it. So the question is that if the limit frequency of Lyman series is VL, here it is not VL, this is actually nu L. Nu means frequency L, I'm sorry, so nu is written like this, nu L is equal to actually frequency of Lyman series. So this is Lyman series. So we have seen that. Okay, frequency of Lyman series. Then the series limit frequency of Pfund series is what out of this four options. Now let us see series limit frequency of Lyman series is nu L given by RC Z square infinity square. So this is the series limit of Lyman series. Okay, this means this is RC. Similarly, series limit frequency of Pfund series, RC Z square 1 by 5 square minus 1 by infinity square. Okay, so this will give you actually RC Z square by 25. Therefore, so this will be nu L by 25. So first option will be the correct option. Now we'll have this question. This is also a very simple question, but this is again, this is from some paper 2014 IIT JEE. Sorry, this is 14 problem 2014. 2014. So here the question is given and answer also you have to give from here itself. The forward biased diode connection is. See, forward bias means what? You have P and N, right? This is P and this is N. Okay. Now, when this is actually effectively positive, then this, suppose this is negative, then it is forward bias. Another way of forward bias, suppose when both sides there are positive, then if this is more positive, then it is forward bias. Now suppose in both sides you have negative charges. Here also negative, here also negative. Then this side has to be less negative. Sorry, this is also negative, this side also negative. That means P and N both are biased by negative batteries. But if this is less negative bias, less negative, okay, less negative, this has to be less negative, and this side after biasing has to be more, sorry, and this will be more negative. So this is how I have see here positive and negative, right? Then both are equal. Can I say anything? No, I cannot say. Okay, here also I cannot say anything. Both are negative, equal negative. Now this is positive, this is negative. Okay, which one is? See, this is positive. I'm sorry, this is also positive. This is actually less positive, this is more positive. Okay, so the question we have to solve here is the forward bias diode connection is. The forward bias diode connection is which out of this? Okay, so as I said, this is positive, this is negative, right? This is positive, already positive is there, and this is negative. This is actually forward bias. Okay, forward bias. When you have both positive and negative, and this side is positive, this is negative, then it's fine. See, here both are positive. If this would have been 4 and this would have been 2, then I would have told this is forward bias. Now in this case, this is -3, again this is -3. So here actually there is no difference between these two. So if this is less, this is -3, and if it would have been -5, then I could say this is forward bias. Okay, further here it is negative, P side is negative and N side is positive. That's why it is reverse bias. This is reverse bias. Okay, so this is how you have to find out whether something is forward bias or reverse bias. Like some connection is forward bias or reverse bias for the case of diode. Okay, so this is actually forward bias because this P side is positive, like connected to positive terminal of the battery, and the N side is connected to the negative terminal of the battery. And other cases, you look this one, it is actually connected. So P side is connected to negative, and N side is connected to positive. That's why it is reverse bias. In this case also, effectively this is more positive than this. That's why it is reverse bias, and in this case both are same, so that's why in this case we cannot say this is forward bias. So if you claim this is the only one which is forward bias diode connection. Okay, I think we'll take one more last question. See, I have to write the question here. Question number 9. The reading of ammeter for a silicon diode in the given circuit is, answers are 13.5 milliampere, then 15 milliampere, 0 milliampere, and 11.5 milliampere. Okay, so the circuit is this is 200 ohm, and you know this okay, so battery is given as 3 volt, and here the ammeter is connected like this. Okay, you have to see the reading in this. So what will be the reading in the ammeter? So this is a question from IIT JEE. Main 18 question. We have solved this question. Let us read once again. The reading of the ammeter for a silicon diode is given the circuit in the given circuit. Okay, so you know what happens when you look, this is actually forward biasing, right? Forward biasing, this is P side, so P, and this is N side. So P side is connected to positive terminal of the battery, so it is forward bias, there will be conduction of current, so there will be current flowing in the circuit, that is for sure. But it is not this current, it is not directly this one, 200 ohm V by R, it is not directly this V 2000, it is not directly 3 by 200. Okay, if you do this, then it will be wrong. I'll tell you, this is 3 volt, then it will be wrong, because see, some voltage, till some voltage in the forward bias characteristics, if you see, your actual current starts from here and goes like this. Okay, this is forward biasing of a silicon diode or any diode, normal diode, in the forward bias characteristics, if you see. So up to this, actually there is a threshold voltage required. kind of threshold voltage, or up to certain voltage, the diode will not conduct because your P side will not have enough forward bias. So it is up to 0.7. Only after, see, this silicon diode will conduct only after V is equal to 0.7 volt. Okay, beyond this there will be current. So you know, you have to actually elapse, or you have to spend this much voltage first to get some current in the ammeter, or to make the diode conduct. In case of silicon it is 0.7. In case of, I think in case of germanium it will be 0.2, like that. So now if you subtract this 0.7 from 3 and then divide that with 200, you will get 0.0115 volt, which is, if you just multiply with 10 to the power 3, then you get 11.5 milliampere. 11.5 milliampere current. So through the diode, or in the ammeter, you will see 11.5. Okay, so the diode reading will be this. All right, with this we will stop it here for today. In the next class, we'll take up mostly questions from digital circuit and this diode and transistor part alone. Okay, so one or two more classes, then we'll finish this modern physics chapter, and then we'll see whether we can pick up much more advanced questions. Okay, so thank you for your patience. Bye for today.